Hi, welcome to the 10th lecture on compactness, part of Topology series. This is probably the last lecture on the series on compactness. There are a few more things which I could say, but I can make them as independent videos later sometime. But whatever I've done in these 10 lectures will be more than what you usually cover in a general course. So that way I think I'm happy. Hopefully you are also happy. Okay, let's get started. So in the last lecture I said many of the results are interesting results are about compact Hausdorff spaces, right? So let's look at X tau to be compact Hausdorff. Okay, do you recall we proved that without compactness itself, if K is a compact subset in a Hausdorff space, then K is closed. Okay, and in the course of the proof we did something just to quickly, as I keep saying, whenever I look at such things I quickly go through the proof, perhaps not with all details, basic ideas. Okay, this is how I become confident of what I'm doing. So this is my K. I want to show this is closed, so give me an X. What I did was, for each Y here I chose an open set. Okay, and then accordingly I had lot of, so for this each Y I had an open set Uy which contains X. As Y where is here, this where is, okay, this we will call as Vy. Okay, so that Uy intersection Vy is empty. Then what it was, Vy is as Y where is over K, this is an open cover of type 1 for K. Therefore we admit a finite subcover. Okay, Vy in F, F is a finite subset. Then we will looked at U equal to intersection of Uy in F. Then this is an open set. What we showed was, okay, let V equal to union Vy as Y where is over F, and this U which is intersection of Uy, then we showed that U intersection V is empty, and this already contains your K. In particular U intersection K is empty, therefore X belongs to U and it is contained in X minus K. And that's how we proved the complement of K is open and hence K is closed. Okay, you see that proof I would have taken about 15-20 minutes to explain. Now within about 2-3 minutes I recall the proof. You keep trying like this, you will become more and more confident. Okay, and do not worry about you don't get 100% correct. You keep on trying, you will see you will succeed. Okay, forget it. So finally what I have done is this. Okay, if X tau is Hausdorff and K is compact and X is not in K, then there exists an open set U containing X and open set V containing K, so that U intersection K is empty. This is what, okay, this is part of the proof. Proof showed this. Okay, I will ask you to quickly again go through. Right, now keep this. Now we are ready for the theorem. Suppose X tau, this is a proposition, is a compact Hausdorff space. Compact Hausdorff space. Right, now let K be a closed subset and X not in K. X is an element, right? So the picture is what I have drawn earlier, right? Then there exists X and K can be separated by means of open sets, disjoint open sets. Do you understand what this means? That is, there is an open set U containing X, there is an open set containing K, so that U intersect K is empty. Right? Now remember what is meant by Hausdorff. You give me two distinct points X and Y, then there is an open set U containing X, another open set V containing Y, so that U intersection V is empty. Right? Remember, in Hausdorff space every singleton is closed. Right? Therefore X, I can say, is not in the closed set singleton Y. Okay, this is more general. Now the K can be anything. Remember, the singleton Y is also closed. Are you following? So we are saying in a compact Hausdorff space we can separate a point, a closed set, and a point not in the closed set by means of open sets. Keep the picture in mind again. Okay, don't just try to memorize. So I have X and I have a K. This is compact plus Hausdorff, and a point X. Then I have an open set here, and I have an open set. Okay, this doesn't. Okay, this is not good. Okay, this is, yeah, this is my U, this is my B, so that U intersection V is empty. Okay, and we just know, we have already proved it. Why we proved it? Because since K is a closed subset, K is also compact, right? And X tau is a Hausdorff space. So what I have shown, in any Hausdorff space, if K is a compact set and X is a point not in K, I can separate them by means of open sets. You understand? Therefore this is immediate corollary of whatever you have seen here, right? Okay, this implies quickly this one. Okay, so pause, review, proceed. In fact, we can prove something more. Suppose X tau is a compact Hausdorff space and A and B closed subsets of K of X, as so that A intersection B is empty. There disjoint closed sets. Then I can separate them A and B via open sets, via disjoint open sets. What does that mean? There is an open set U containing A, there is an open set B containing B, so that U intersection B is empty. Again, keep the picture in mind. Okay, this is my A and this is my B, and this is compact Hausdorff. Then what do I want to say? There is an open set U and there is an open set B. This is B and this is U, so that U intersection V is empty. So A and B are separated. Okay, the proof is again easy. It's just the earlier argument. So let's start. For each A in A, I know that there exists an open set UA containing A and VA containing B, such that UA intersection VA is empty. Why? Because remember, A and B are closed sets in a Hausdorff space, and take a little A, right? Since B is a closed subset of a compact space, B is also compact, right? Therefore P is a compact subset of a Hausdorff space, and point A, since the sets A and B are disjoint, the point A is not an element of B. Therefore, by just now the last result, there exists an open set. There exists open sets U and B, which is separate the singleton A and the set B. So we are calling them as UA and VA. Is that clear? This is by the last result. Right? So here, to get this, what did we use? We use the compactness of B. But remember, A is a closed set. Therefore, A is also compact. Right? Therefore, I have to use the compactness hypothesis for A. That means I have to find an open cover for A and extract a finite subcover. I am sure all of you can think of what is the open cover. Yes. Look at AA, UA as A in A. This is an open cover of the compact set A. Why A is compact? Because A is a closed subset of X and X is compact. Any closed subset of a compact set is compact. Therefore, this is compact, right? Therefore, there exists a finite subcover. Okay. Remember, there are always people who are very pedantic. What happens if A is one of them is empty or both of them empty, etc.? You can see all cases are easy cases. Suppose A is empty, okay, then I can take U to be empty set, B to be all of X. Therefore, X intersection empty set is empty. You understand? So such a trivial case I don't work. Okay, I am just looking at, I am assuming A and B are non-empty closed sets. Okay, you follow that? Now what should be my U? See, this is an open cover, therefore I have an open set, namely UA as A in, UA as in A is in F, right? And what should be the open set which contains B? Remember, for each in A we had a VA, right? That's an open set containing B, right? Therefore, as A varies over F, VA, this is a finite collection of open set. Therefore, I can define B. Can you guess what should it be? We had already seen it. Yes, VA, A in F now. So for each A, VA is an open set containing B, and finite intersection of open sets is again open, right? So this is my definition of VA. So it's clearly my A is contained in this and B is contained in this, because B is contained in each and every VA, therefore it's contained in intersection VA, right? Now what remains to be shown? So we have to prove U intersection V whether it is empty, right? Suppose X belongs to U intersection V. What does it mean? It says X belongs to U and X belongs to V, right? X belongs to U. What does it mean? X belongs to union UA A in F, and X belongs to VA for every A in A, correct? This means there exists an A in A F so that X belongs to UA, right? And remember, my X belongs to VA for every A, therefore X belongs to UA. If you want to call it, let us call for alpha in F, X belongs to U alpha, therefore X belongs to U alpha as well as V alpha, because X belongs to VA for every A in A and alpha is an element of A, therefore it belongs to this. But what was our assumption? For every alpha in A, my U alpha and V alpha are empty. This is a contradiction. Okay, so what does it show? It shows that U is an open set containing A, B is an open set containing B, and U intersection V is empty. So what has happened? I am given a compact Hausdorff space to disjoint closed sets, then I can separate them by means of open sets. Always think and do not remember the words. Whenever I say something, I'm imagining that picture. I have X, I have A, I have a B, and I'm drawing U and B and separate them. Okay, that kind of picture you should have. You should develop that habit. Okay, so pause, review, proceed. Now the third result of this lecture is analog of nested interval theorem. From real analysis. What does it say? I have a sequence of closed and bounded intervals in R. Right? Now remember, therefore it's a closed and bounded subset of R by Henry-Borel theorem. Therefore we know they are compact set. Okay, each Jn is a compact set. Not only that, okay, and what we know is it is decreasing sequence, nested. That means Jn plus 1 is contained in Jn, right, for every n. Okay, Jn is decreasing sequence or nested. Then what is the nested interval theorem? There is also a hypothesis, a metric hypothesis which talks about the length of the interval, but I don't want to worry about. We are in the general topological space, so I don't want to worry about. Let me look at only compact set. Then what do I know? The theorem says intersection Jn is not empty. That means there exists X in a R so that X is in Jn for all n. This is the nested interval theorem. Right? Okay. Only to prove the uniqueness part, I need some metric condition that the length of Jn's are decreasing to 0, but let's not worry about. So actually the importance of nested interval theorem, not uniqueness, it's the existence. Intersection of Jn is not empty is the most important thing. If you've seen my videos on real analysis, you will realize that. Anyway, okay. Now, what can I think of an analog? So I have a topological space X A, and let Kn be a sequence of compact sets, right? And it should be nested. What does that mean? Kn plus 1 should be contained in Kn for each n. Then I will, and of course this should be non-empty, because if one Kn is empty, then intersection will be empty. Therefore let's assume Kn is non-empty for all n. Right? So I would like to know, can I conclude intersection K is not empty? This is a question. This will be analog of nested interval theorem. Yeah? Let us try to do that. Suppose I want to prove this. Okay, there may be some hypothesis needed, but as I'm going to figure out what kind of condition I need. Okay, suppose it's empty. Okay, let us prove by contradiction. That means let us say Kn is empty. Then what will I know? That take the complement, that means Kn complement union, that must be all of X, right? And X is at present topological space, no condition, right? So I want to use compactness somewhere, right? So since so that means I would like to look for open cover. You understand? Now what is our natural choice of open cover here? Since Kns are compact, you would like to say Kn closure, if you call it as un, these are all open. Then I will get an open cover. But do I know Kns are closed? They may or may not be closed in a general topological space. But what do I know? If X is Hausdorff, each compact set must be closed. Therefore, now I put an extra condition, this is a Hausdorff space. Right? Okay, if that is a Hausdorff space, this becomes open because each Kn is closed, therefore, right? Therefore, this is an open cover of X. But remember about X, I have said nothing. Now I have only put extra condition Hausdorff. But I have to use compactness, right? So what can I do? let's look at all my kns are compact and k1 is the largest set in this collection, in this sequence, right? Therefore I can think of this is an open cover not of x, as actually of k1. Do you understand that? And notice that since kns are decreasing, uns are increasing. That means un is contained in un plus 1, right? Kn plus 1 is contained in kn. Therefore by taking complement, kn plus 1 complement, okay, contains kn complement, that is un plus 1 contains un. Okay, right. So since k1 is compact, what do I know? We had already seen this kind of arguments. Okay, there is a finite subset f of n, so that my k1 is contained in un as n varies over n varies over f, right? But since these are all increasing, this is equal to some un, where n is the maximum of n in f. It is a finite set, therefore maximum exists, right? Have you understood? Okay, right. Now let's look at k1. Therefore k1 is contained in un, but that is x minus kn. Yeah, but remember, what is the relation between kn and k1? Kn is contained in k1. Therefore what do I get? I get kn is contained in x minus kn, that is k capital N. This is k capital N complement. Okay, don't say it's a contradiction immediately. Okay, don't say it's a contradiction. We still have not used part of the hypothesis. What are the hypotheses we needed? Just go back. X is substar. Have I used it? Yes. And kns are decreasing. Have I used it? Yes. Kns are compact. Have I used it? Yes. One more hypothesis remains. What is it? Each kn is non-empty. Now comes the problem. Okay, since kn is non-empty, there is a p in kn, right? Therefore the p belongs to kn. Since kn is contained in that means p belongs to x minus kn, but this means p does not belong to kn. Now that's a contradiction. Yeah, do you follow that? Therefore this contradiction shows intersection kn must be non-empty. There is also another way of arguing. Remember, if a is a subset of b, then a intersection b is a, right? Now let's look at it. Now I know kn is a subset of un, which is kn complement, right? Therefore kn intersection kn complement must be equal to kn. But kn intersection kn complement is empty. Now I don't worry about anything. Yeah. Okay, so I have proved kn is empty. Now that's a contradiction, because by assumption each and every kn is non-empty. Are you following? So I have given two different proofs to arrive at a contradiction. Two different ways of arriving at a contradiction. Yeah. Okay, that's about it. So these are all the things. If there is anything more, of course there are more, as I said, I will make them as separate videos. Okay, for example, we proved Heine-Borel theorem. I wanted to show applications which are the conic section, which are the quadratic surfaces, and in the set of matrices, n cross n square matrices, we have a lot of subspaces, right? Subclasses of matrices, which of them are compact, which of them are not compact, all these examples. And also one of the most interesting application I always like in compactness is give me any two norms on Rn or any four-dimensional real vector space, they are equivalent. That is, norm induces a metric. For the metric I get a topology. Okay, so in whatever norm you chose on Rn, the topologies will remain the same. That's something fantastic result. In fact, in functional analysis, you will keep on using this, even though many teachers will not explicitly point out you are using this. They will prove it. in the beginning of the course they will forget to emphasize. Okay, we are using it, forget it. So these are the applications. I will possibly make them as a separate videos later. Okay, I hope you enjoyed, and this concludes compactness. I will come up with something else later. Thank you for listening and watching. Okay, Merry Christmas and Happy New Year. Take care, stay safe.